Right. So what I'm going to talk to you about, as Tom mentioned, is more my experience with unfired earth, and specifically with rammed earth, at the beginning of my career, and then for around 10 years. The 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 image, I actually thought of starting with this image, which I find is probably I would say probably like our stereotypical collective imagination image of what Ramdeath is. So it's generally self-built, it is used in self-built projects, or in emerging markets. There's no need for advanced machinery. It's extremely labor intensive, and because unfortunately labor is still quite cheap in these countries, then yes, we can use it there, and not necessarily in the Western world. And there's no need for skilled technical knowledge, etc. And by the way, this is a project I worked on myself in Benin some years ago. So I'm not really bad mouthing anyone, but I just really wanted to show you, okay, what I think people generally would tend to think about rammed earth. And what we might tend to not know, though, is that rammed earth has been used in parts of the Great Wall of China in Shandong, and according to the National Geographic, this is 2,500 years ago that was built, and it's still standing and still in good conditions. And the other very iconic building that I'll show you today is the Alhambra in Granada. A lot of you might know this building, and it's actually it's been built around between 1200 and 1300, and it's made out of rammed earth, as you can see, but the construction technique specifically is called calicostrado, which is a technique that, similarly to what Anthony has shown to you today with Cobauge, divides the wall into two different layers. So you have a rammed earth layer, which is unstabilized, and a rammed earth layer that is stabilized with lime towards the external side of the wall, quite typical of that period. And this is is an extract of a very beautiful book called La Restauración de la Tapia, so the restoration of rammed earth in the Iberic Peninsula, that I really recommend if people can speak Spanish. I don't think it has been translated. But this is really to show you how many different rammed earth techniques can be used and have been used throughout the past, just by changing the blend, just by changing the erosion breaks and the material that was used for the erosion breaks, etc., but slightly changing the way it is manufactured, etc. So it can really show a lot in terms of this technique. There's a lot to say about history of rammed earth, but I'm not going to deal with that a lot. Just touch on François Cointreau, which is an architect that lived between 1700 and 1800, and he wrote a book in French on how to build with rammed earth. And this book, for some weird reasons, was then translated into almost all European languages. It was even translated in Danish, in Russian. It got to the US, etc. So it really brought a sort of revival of rammed earth at some point at the end of 1700. But the other thing we might not necessarily know about rammed earth is that is currently being used as a construction material for contemporary buildings in Europe and beyond. And there is plenty of examples of rounded and contemporary architecture, and also that this technique has been industrialized. Sorry, I'll just go back to that because I'll probably have we'll probably have to have another session at some point where I tell you all about the stories of the different projects that I'll show you today, but we won't have time to go into the details. But just quickly, this is a cinema in Ilanz, in the mountains, in the Swiss mountains. So not only the walls are made of brown earth, but also the floor is completely made of brown earth, and the cladding to the steps up to the exit door, and the ceiling is a clay plaster, as you can see. This is Plaza Pingia. This is a single family house in Almens, again in Switzerland. Sigi has extensively talked to you about thermal mass and the ability that that unfired earth has in terms of that. So I won't go into the details, but this project is really sort of showing how thermal mass works, because obviously like the stuff that you can see, but also the embedded wall heating in all the walls that you can see here. The ornithological center, in very simple words, it's a birds center. It's a bird station. This is in Sempach, also in Switzerland, and it sort of combines the use of timber and the use of clay, both indoor and outdoor. This is a big project in Daran, in Saudi Arabia. This is a 250 meters long wall, showcasing a seating niche as well, and in the exterior, but like undercover. And then there was a whole big part of internal partitions and internal cladding as well that form part of that project as well, out of round earth. This is a school of agriculture in Mezzana, in the south of Switzerland, in the Italian canton. And obviously, it's quite peculiar to see round earth covered in snow. So I just wanted to show you this specific picture. And then we will talk about durability a little bit more later on. This is the house of Martin Rauch that he built for himself. And it showcases round earth on the exterior, so completely exposed, but also in the staircase on the interior, where he decided to have a double layer. And there's probably a whole hour to be spent talking about this pioneering project, because it's extremely interesting to see the different construction techniques that have been put in place and executed for this project. So we'll have to do it another time. But as Tom was telling you, I had the chance to work with Lehm Ton Erde, which in German means loam clay earth. Right at the beginning of my career, when I started getting really passionate about unfired earth. And they are based in a valley in between the Swiss and the Austrian mountains. And the studio, as you can see, is on the left hand side. Used to be a very tiny little studio that was shared also with the ceramic studio that his wife used to run. And then, so Martin is actually a ceramist in terms of his background, but then he spent more than 35 years now, because time is flying, developing rounders as a technique. And so on the right hand side, you can see what is his workshop now, recently built in 2015, where he prefabricates rounder elements, and we will look into that a little bit more in detail later on. And he had the chance to work also with really renowned architects such as Lehm Ton Erde and Snoeta. So momentum has been picking up since, I would say, probably 2010. That's when he first started doing really big jobs with star architects, etc. So back to the technique itself. How do we actually execute round earth? So the first aspect is obviously the blend and the component, and the first step is finding the right components. The tendency is to use 70% of the site excavation material and approximately 30% of the nearby seams or quarries. We often manage to find quarries in a very small radius around the building site, so it's generally quite easy to find the right materials, not so far, and to avoid long transports. The first sort of so this I would say this aspect of finding the components. So the first aspect is called subsoil or clay winning or earth winning. This is how it's generally called. And then this is called stockpiling, and it's when the material is left to weather. This generally helps to break the material lumps down to smaller pieces using just the nature and the water and frost, etc. So it's not necessarily a must, but it just helps out with the next step, which is the mixing. And here you can see the blend composition of one of the projects that we worked on. I would say, so there's a lot of stuff to be said about the blend itself, but I would say around 80 to 90% of the blend in round earth is aggregate. And aggregate doesn't only mean sand and silt, but it also means gravel for round earth, and specifically quite chunky gravel to a granulometry of 35 to 40 millimeter. So just compared to a cob material, for instance, it doesn't have fibers, so it uses aggregates. We will look at the water content as well later on. And the amount of clay is extremely reduced. So you would have an amount of between 20 and 10% of clay, so very, very small clay amount. And this is to avoid shrinkage, so to control shrinkage throughout. And actually the water content, sorry, no, this is a completely different subject, so I will finish off here. So the very low water content, approximately 8 to 10% to clay weight, allows shrinkage to be very, very low in round earth, between 0.25 to 1%, which in comparison to standard, for instance, shrinkage in ceramic clay or in brick clay, that can go between 5 and 15% is actually minimal. I'll digress slightly about stabilization, just because it's a big topic. For those that don't know the difference between a stabilized and an unstabilized round earth, we call stabilized round earth when the blend is composed of between 8 and 13% of cement or lime. The cement or lime replace the clay. So the type of binding that they create is a completely different binding. Clay creates electrical bindings, and cement creates a chemical binding. And what clay allows, well, it has positive and negatives, obviously sides to that, is that the chemical binding doesn't allow water to have an impact on the binding once it has occurred, in comparison to obviously what clay does, that can be still malleable if water is added once it's bound. And the reason why round earth is stabilized, and that happens, it happens very often in Australia, very common in the US as well, stabilized round earth, is mainly for two reasons, for compressive strength and for weathering performances. So I've just put here a couple of numbers just to give you an idea. Unstabilized round earth can have a compressive strength of 2.4 Newton per square millimeter. Concrete has between 30 and 40 Newton per square millimeter, while stabilized round earth has between 5 and 10 Newton per square millimeter. So compressive strength is one of the reasons why round earth can be stabilized, and the other is obviously the weathering performance. So just what I mentioned before, the fact that the chemical bond is not impacted by weathering once it's occurred. But what we don't tend to think about when we think about stabilization is, I would say embodied carbon is something that everybody would think of, so I won't touch on that. But what we don't tend to think about is the hygroscopicity. So what Siggy was just talking about in terms of the ability of the clay and the earth. I shouldn't actually talk about clay too much because there's very little clay in it, but the ability generally of this material to inhibit and sort of to regulate passive humidity and in a passive way. And this is sort of inhibited in a way by cement. So that's one thing that is not necessarily thought about. The other thing is the reparability and the aesthetics. So on the left-hand side, you can see very little holes in the wall. These are called tie holes, and there's like sort of vertical and horizontal lines that are called formwork lines. And this just happens because the material cannot be reworked once it's set, because it's bound with cement. So all these imperfections would remain visible. While on the left hand side you can see a massive wall where sort of no imperfection is shown. It sort of really stands out in terms of aesthetic. And then the other aspect really important is the reparability. So the ability of taking exactly the same material and ramming it in place when there's a problem. And then also over time is an incredible aspect that we never think about when we stabilize. And then obviously we haven't talked about expansion joints. There's a lot to say about that, but the thick horizontal line that you can see in the middle of the image on the left hand side is an expansion joint, and that's used in cement, in concrete facades, but also in all brittle facades, right? So in bricks facade, in ceramics facade, etc. to do two things. So one is to prevent the cracking during the initial drying phase of the material, which is irreversible. So there is an irreversible shrinkage that happens at the beginning when the material loses water. And the second one is to sort of accommodate the movement of thermal expansion and contraction by exposing the material to external weathering. And that whole aspect of expansion joints is not at all a thing when we deal with unstabilized rounders. And then the other thing is obviously recyclability. When you don't stabilize, you can take the material, bring it back to the pit, and at the end of its life cycle, and it's 100% recyclable. I want to show you just very quickly. I know I would probably run over looking at at the time, but let me know if I need to speed up or not. Sorry, I get Teams messages. So one thing I wanted to show you is the erosion. So the weather performance of rounders throughout, and the durability of rounders. This is an image of the facade of Haus Rauch that I showed you today in 2008, and that's exactly the same facade in 2010. So you can see how the material has eroded. And there is a process that we call calculated erosion that I will quickly explain here by use of these graphics. And it's mainly due to the fact, so what happens is that the external edge of the facade during the first 3 to 5 years of the life of the building is eroded away. And that mainly happens due to the fact that during the compaction of the material in the formworks, there is friction between the formwork and the tamper or the rammer, pneumatic rammer or electric rammer that we use. And that sort of like gives a loss of compaction towards the end of the formwork. So the edges are looser in a way, and they tend to erode throughout the first few years. But this is calculated when we execute rounders. And on so what you can, so the graph really shows that it's a non-linear erosion. So that means that it erodes quite a lot and extensively during the first few years, and then it gradually stops for that reason, because the material is actually properly compacted towards as we get into the formwork. And then these are erosion checks, we call them, and it's they can be made of different materials. We won't go into that detail, but what they do is they have two different sort of functions. The first function is to reduce the speed of erosion. So when instead of having a wall that is eroded very quickly, the erosion happens where the erosion check is, and then it sort of is forced to break around the erosion check. And the other reason why we use erosion checks, and they've been used forever, so since the beginning of this material, and when it's so it's a very traditional thing, is they tend to spread the material over to the next layer. So what all the clay that is eroded on the top is then stops here, and then it sort of spreads out throughout the second, so the bottom layer. So in a way, it has these two functions, but and it can be the erosion check can be made of different materials. So going back into manufacturing, this is the blend preparation. so we looked into blend, etc. So we once the material is ready, it gets mixed into the hole. It's weight controlled, and water is added to it if necessary, depending on the water content. We generally use wet pans, like typical wet pans, to mix it as well. This is just to show you both the particle size distribution and the water content of the material. You can see the material is extremely dry in comparison to the majority of the other techniques that you would use with unfired earth. And the size distribution is very important, so that going from a 40 millimeter gravel down to clay, it's very important that this distribution is quite even in terms of granulometry. This is just to show you the difference between a traditional formwork and a more contemporary formwork. The traditional formwork is generally made out of wood, but there's definitely a lot of different options there. Contemporary, so this is a formwork that uses so it's Doka formwork, that is a very standard aluminium formwork system, modular system, super light, used by mainly developed by the concrete industry, so used throughout the world. And it's been specifically developed for rammed earth here. I say just, but actually it's been a work and a development that has been lasting for many years in terms of trial and error sort of development. So this is actually quite a big thing that has been happening in the last years at Lehm Ton Erde. And this is the pouring of the material. So traditionally you would use buckets, and then obviously now we tend to use either scrapers or excavators or little bulldozer to fill in this distributing machine, which is actually helping distributing the material throughout the formwork. Instead, on the right hand side, you can see much like the sort of the traditional way, measuring with a measuring tape, and which is totally feasible. It just takes forever. And then the compaction is done in 2 steps. So there is a first, traditionally so you just using feet, compacting by using feet, and then using an iron head hand rammer. While on the left hand side you can see the typical road like the mini rollers that you would see compacting cement on the street, is being used in the formwork. And then there is a specific machine also that has been developed here. And then there is a second step to that, which has to do with the calculated erosion that we talked about, which is going around the edges and really trying to compact all the edges much more, because this is where the erosion will have an impact. Obviously, on the right-hand side, wooden pole with the tip, so this is quite important. And then on the left-hand side, pneumatic rammer. This is the striking, it's called this. So it's the deshattering process. It's when the formwork is taken off, and if we compare that in comparison to a concrete prefabrication, obviously you have to wait until the concrete is set to deshatter or to strike, while here the striking happens straight away. On the right hand side, there's a typical in situ fabrication, where you would have the 600 millimeter lifts that Anthony was talking about before with cob, and then you would sort of strike and then move the same formwork up to the next level, and that continues over and over, going around the building. these massive tie holes that so these holes that you can see here, these are called tie holes, the same that we saw in the stabilized rounded image before, with the difference that here, because it's unstabilized, you can refill them with the same material, so they won't be visible at the end. While on the left hand side, you can see prefabrication elements, and they are here striked, and then they are moved to the drying area. What I would say, this is probably quite self-explanatory what prefabrication brings. We talked a lot about the seasons, and the fact that the sort of the seasonality of the construction. I suppose I think Anthony was talking about this when talking about Coboj, and obviously with prefabrication you're completely independent from seasons and weather, etc. Cost is a big thing, so you obviously become much more cost competitive because it's less labor intensive, and it's the coordination on site is much easier because the blocks are brought to site when dry already, so there is just the installation site, etc. There's a lot of aspects also associated with the trades coordination and with the construction process as well, and the speed of construction. So here you can see the curing, as I said, because it's the water content is very low. The curing is quite quick for 45 millimeter, 45 centimeter thick elements. This element here that you can see is approximately 1.2 by 3 by 3 meters by 45 centimeter, to give you an idea. But the sizes obviously vary depending on the facade, etc. Then the elements are then brought to site, and then they're installed almost like Legos. They are sort of like strapped with ratchet straps, like very typical of building sites and construction. This lifting beam element has been is a bespoke lifting beam element that has been developed. And then the vertical alignment is being done by chain hoists. We only use clay mortar to lay the blocks onto and in between the blocks. And then the joints, as we were saying, are being filled with exactly the same material. So it's just a question of having the sort of the elements to get them a bit wet, a bit moist, and then rerun exactly the same material in the joints. And this is the only aspect that is still being done by hand. It's quite difficult to mechanize that. And then here you can see it's almost like having a little rubber. You can see the joints sort of disappearing on the facade, and this is the finished facade that really looks monolithic. Thank you.
Brilliant. Thank you so much, Laura. That was absolutely fascinating, and it sits well, I think, with the other presentations we've had this morning. This afternoon, rather. Maria